vector spaces have subspaces, and groups have subgroups. Here's the definition of a subgroup. A subgroup of a group G, whose binary operation is star, is a subset H of G with the following three properties. First of all, it's got to contain the identity element of G. Secondly, it's got to be closed under multiplication. What that means is if you have two elements x and y in H, then x star y is in H. So this property is called closure under multiplication, or closure under the group operation star. Finally, if x is in H, then the inverse of x must be in H as well. So this property is called closure under inverses. And there's a special piece of notation for when a subset H of G is a subgroup, which is exactly like the notation we use for subspaces. So we use this notation to mean that H is a subgroup of G. Another way of saying this definition would simply to say that H is a subset of G, which is itself a group under the same operation that G was a group under. So let's look at some example subgroups. First of all, there are two boring subgroups in every group. First of all, the identity on its own forms a subgroup of G. That certainly contains the identity. It's closed under products because the only two things you can multiply together are the identity times the identity, and that's the identity again. And it's closed under inverses because the inverse of the identity is the identity. So that's a subgroup. Also, the whole group G is a subgroup of itself. And next, another example we've seen, the alternating group. So you'll remember that that consists of the set of even permutations in Sn. This is a subgroup of Sn because, as we've just seen, it's a group. The collection of integers, or the set of integers, is a subgroup of the group of real numbers under addition. That's true because the integers contain the identity element 0. They're closed under addition because the sum of two integers is another integer. And they're closed under taking inverses because the inverse of an integer a is minus a. And if a is an integer, then minus a is an integer. So on the other hand, the natural numbers would not be a subgroup of R. So with my definition of the natural numbers, they contain 0, so this would pass the first part of the subgroup test. It does contain 0. It's also closed under addition, because if you add two natural numbers, you get another natural number. But it's not closed under inverses. Because, for example, 1 is a natural number, but minus 1 is not. Our final example is a subgroup of the group of integers under addition. And when we use this symbol 4z, what that means is the set of all multiples of 4, all integer multiples of 4. And that thing is a subgroup of the group of integers under addition. So again, let's check the conditions to see why this is true. So why is this true? Well, for sure it contains 0. So 4z, 0 is equal to 0 times 4. Let's write this as 4 times 0. So that's an element of 4z. That means we've passed the first of the subgroup tests. Next, we need to show that it's closed under addition. So we'll take two elements. 4x and 4y are in 4z, where x and y are integers. Well then in this case, if we add them together, we can factor out the 4, and you get 4 times x plus y. Now x and y were integers, so x plus y is an integer, so this is 4 times an integer, so it's an element of 4z. So we've shown that if you take any two elements of 4z, add them together, then you've still got an element of 4z. That means 4z is closed under addition. Finally, we have to show closure under taking inverses. So we take an element 4 times x in 4z, where x is an integer, then its inverse is minus 4x, and we could rewrite that as 4 times minus x. Now x is an integer, so minus x is an integer, so this is 4 times an integer, so it belongs to 4z. 4z contains 0, it's closed under addition, and it's closed under taking inverses, so it is a subgroup. There's a special kind of subgroup which is often very useful to us, which is called a cyclic subgroup. So here's the definition. We take G to be any group and lowercase g to be any element of G. Then we write pointy brackets G like this to mean the set of all powers of the group element lowercase g. Now that is a subset of G for sure, because these powers are just this element G multiplied by itself, or the element G's inverse multiplied by itself. So it's definitely a subset of G, and in fact it is a subgroup of G. So that's what we're going to prove in this lemma. We'll prove these pointy brackets G, which we call the cyclic subgroup generated by G. We're going to show that this really is a subgroup. So to check that, I have to verify the 3 parts of the definition of being a subgroup. First of all, it's got to contain the identity. So if we use E as usual to refer to the identity element in G, then pointy brackets G needs to contain this identity element E. But it does, because it's G to the 0. So G to the 0 is by definition the identity element, so G to the 0, which is equal to the identity element, belongs to pointy brackets G. Next, we're going to show closure under multiplication. So we take any 2 elements of this cyclic subgroup. So those are G to the A and G to the B for some integers A and B. But then when you multiply them together by the exponent law, what you get is G to the power A plus B. So that is an integer power of G, so it belongs to the cyclic subgroup. And finally, if you take an element in the cyclic subgroup, G to the power A, then its inverse, as we saw when we introduced powers, is G to the minus A. But that's another integer power of G, so it's an element of the cyclic subgroup. So we've passed all 3 tests, and so the cyclic subgroup, in inverted commas, really is a subgroup. We can say a little bit more about these cyclic subgroups. In fact, we can say what their size is. And the claim is that if you have a group element G, then the size of the cyclic subgroup generated by G is equal to the order of G. So let's see why that is true. So of course here we're assuming that this group element does have an order, that it has a finite order. So let's say that this order of G is equal to n. So then what we have to show is that the size of the cyclic subgroup generated by G is n. So this cyclic subgroup was defined to be the set of all integer powers of this group element. But we know something about those integer powers because we investigated them at the end of the final video. So there are 2 results. First of all, every power of G equals 1 of G to the 0, G to the 1, G to the 2, up to G to the n minus 1. So that means this cyclic subgroup has got size at most n, because every single power of G, everything in that cyclic subgroup, is equal to one of these n things. But point 2, we showed that the elements E, G to the 0, G to the 1, G to the 2, up to G to the n minus 1 are all different. since they all belong to this cyclic subgroup, its size is at least n. Its size is at most n and at least n, so its size is n. And we're done.